Okay, I dropped a ball on the floor, much like this one. It bounced up, didn't bounce up as far as I expected. And being old and not completely warmed up, I didn't quite get to it, so I didn't catch it. I'm going to catch it this time. Okay, here it goes. It's going to drop. I'm ready for it. I wasn't expecting to have to bend over. Okay. Ball dropped from 1.5 meters. It's floored about 5 meters per second. Now, you know the work that gravity did on it is mg times 1.5 meters, right? And its kinetic energy when it hits then is going to be equal to that. So you set 1/2 mv squared equal to all that. And you could figure this number out, or you could just say 1.5 meters accelerating at 10 meters per second squared roughly. What speed does it get? And you get the square root of 2a times the delta s over square root of 2 delta s over a. Okay, so anyhow, the ball dropped from there. It's at about 5 centimeters per second. So we want to know what the average force of the floor on the ball is because the ball then bounced up. Okay. Not only bounced up, I would guess about 60 or 70 centimeters. Lost most of its kinetic energy. We'll talk about that situation. So what's the average force of the floor on the ball? Well, during compression, the ball travels 1 centimeter. Velocity from 500 centimeters per second to 0 centimeters per second. Okay. So the average velocity, you might have trouble reading that. I'm writing a little bit fast. The average velocity is not much different. I said not far from, which is kind of not quite the right way to state it, but you understand what I mean. It's pretty close to 250 centimeters per second. It's going from 500 to 0. Now, acceleration is not uniform. It won't be exactly 250 centimeters per second. I'd say plus or minus 50 centimeters per second until you make other assumptions, like the force of compressions, like the KX thing, maybe. But you don't know how to deal with that now. We haven't developed that. So we'll just go on with average velocity, 250 centimeters per second. Four milliseconds, 0.004 seconds. Now, while I have the balance turned on here, I can measure the mass of the ball. There it is, 25. It's 26, but we'll use 25 because it's easier to calculate with. 25 grams. Okay. Well, the average force times the delta T is equal to the change in MV during that delta T. And that would be net force. Okay. So what information can you use to get something related to F bar delta T? What do you know? In this equation, do you know delta T? Well, during contact with the floor, that's 1.04 seconds, right? You know delta, well, do you know M? Well, yeah, I just put the thing in the balance. I said it's about 25 grams. Okay. You know the change, do you know MV at the start? Well, at the start of that compression, it's moving at 500 centimeters per second. I use 500 centimeters per second because we have a 1 centimeter compression. It's easier to think about 1/500th of 1 than it is to think about dividing 0.01 meters by 5 meters per second, but it can work either way. Okay, anyhow, you know, just so calculate real quickly, just calculate the change in MV. Very simple. You can use a 5 meters per second if you want. Or you could use a 500 centimeters per second. It's easy either way. Okay, I did something really bonehead. You should have erased a little bit in this one. But fortunately, I didn't record it, so I can pretend I never did it. But anyhow, your initial velocity is negative 5 meters per second. I'm choosing upward as positive. And mass 0.025 kilograms. You multiply that, you get negative 0.125 kilogram meters per second. I'm thinking I put a 1/2 in front of this. So got half that 0.0625. That's what I did. I admit it. But there it is. Okay. Now, what's ZF? For the compression part before it rebounds. 0. It stops. Okay. The delta MV is MVF minus MV naught. MV naught's negative. It's plus 0.125 kilogram meter per second. Now you want to always be thinking about signs because it's real easy for signs to get confused. One of the probably the most frequent error mathematicians and computer scientists and physicists make is a sign error. So easy to make. So be careful. And then think, is that reasonable? Is a change in momentum in the upward direction? Okay. I'll ponder that. Now, so I know delta MV and I know delta T. Geez, how am I going to find the F? Okay. Now I've got F net delta T equals delta MV. And we'll stick with it. Okay. So what's F net? Delta MV over delta T. Which is, we can easily calculate it. your delta t is 1/250th of a second. So when you divide by 1/250th of a second, you got to get 250 times this. Okay, which is going to give you 375 newtons, which is close to 90 pounds. If I've got my decimal in the right place, I think I do, yeah, 3750. Multiply that by 1,000, get 125, so, actually, I'm saying it comes out 37.5. Yeah, it does. That's probably wrong. Order of 250. That'd be if it's 1.5. I'm going to get confusion now. In the ballpark of 30 newtons. And ballpark is good enough because all of our estimates were ballpark. Okay. Like I know that average velocity isn't 250 centimeters per second. We can figure out if it should be a little more, a little less by the fact that the average force is increasing. But we're not going to go to that trouble. This is an estimate. And if it's 20 newtons or 50 newtons, it's not that far off from 30. A lot more force than you'd expect. Make sense? Then you can check that. With a 30 Newton force exerted through 1 centimeter displacement give you a velocity of 5 meters per second. Or do I have a decimal place off somewhere? Okay. So I can say you can check. Okay. Does that make sense? Quick calculation will tell you whether you had it right. I mean, you can certainly figure out what the acceleration is, right? 30 newtons divided by 0.025, which is 1,200 meters per second squared, about 120 Gs. Okay. So you want to think through stuff like that. All right. What I'm showing you is that this is one thing the impulse momentum theorem is good for, and you're going to see it in the problems. I should have mentioned it last time. Just didn't think of it at the right time. Okay, I'm just going to wave my hands on this one. You got the output machine. We've taken measurements. We've measured how far it falls. We've measured how long it takes to descend from rest. From that, we can calculate, number one, the work done by gravity. Just take the work gravity does in one mass and work gravity does in the other mass. One of them's going to be positive, that's this one, and the other is going to be negative. And the positive work is going to exceed the negative because it's the greater mass that descends, greater force descent. So all that should be pretty clear, but make sure you really pull that together in understanding the output machine. One reason being that this output machine is going to lead us, it almost has, whether you know it or not, it's going to lead us to the whole idea of moment of inertia and angular energy, angular kinetic energy, torque, and all that stuff. Okay. Okay, so that's a digression, but that's from the Atwood machine. But we calculate the work done by gravity. We can assume the acceleration is uniform and calculate final velocity and the height. Distance it falls. From the final velocity, knowing the mass, what can we determine? Well, the first answer I got was momentum, because we just were talking about momentum, right? So that's a good answer. But really, we're also talking about the work done by gravity, and that isn't related to momentum in any direct fashion. That's related to the change in kinetic energy. Okay? So we could calculate the change in kinetic energy based on the time it takes to follow a known distance from rest. We calculate the final velocity, just calculate the average velocity. And since the average and final velocities, since the initial and final velocities give you the average velocity, add them, divide by 2, and the final velocity is 0, well, you immediately get the final velocity. And use that to calculate your kinetic energy. Okay. You can also calculate your energy using the work energy theorem. Again, you know the mass, and you know the work done by gravity. Okay. Change in kinetic energy should just be equal to the work done by gravity. And then, of course, you could use the mass to find what the final velocity should have been. What are you going to find? Well, the pulley's a little glitchy. It kind of speeds up a little and slows down a little. I think that's going to tend to suck energy out of the system, which means that the time of fall is going to be a little bit longer than it would be if you had an ideal pulley. And you want to think through what that means and what that tells you. Okay? So you want to understand the Atwood machine at that level. Because again, we're going to do some more accurate measurements and do some stuff Black Friday. With the beam and the descending mass, we do all the same things. So we're going to talk about that for just a minute. Okay, we're talking about a mass descending tied by a string to a pulley. It rotates about an axle, and to that pulley we have a beam attached. If we time the mass in its descent and know how far it descends, we can easily figure out its final velocity. And now this is what we just talked about with the Atwood machine. Okay. Now the difference here is that on the other side of the pulley, well, there are two pulleys. There's a pulley attached to the beam, and there's a pulley that the string runs over to the descending mass. On the other side of the pulley, at the mass, this pulley here, where the string goes like this. On the other side, we don't have an ascending mass. We have a rotating beam with some magnets on it. Okay, magnets are just there because that's mass. It's easy to attach. If we know the final velocity, that descending mass, which again we get just by simple timing and measuring the distance, and assuming it's uniform, the acceleration is uniform, and that acceleration is much more uniform than it is when we use these pulleys with two masses in the 50 to 100 kilogram range. Okay. And we maybe want to analyze that, but it just comes down to there's less. Okay, get that speed. So what does that tell us about the rotating system? Well, it tells us how fast a point on the rim of that pulley is moving. It's moving at the same speed as the descending mass. Okay, because in order for the mass to descend, well, it descends a distance equal to the amount of string that unravels from the pulley. at a given time. Uh, there's a clear relationship between those two velocities. I need a picture to say much more about it, but that should be something we understand pretty well. It then turns out that if we know the speed of the point moving around the rim, we know the angular velocity because we can measure the diameter of the pulley. Okay, we can use the idea of a radian distance along the rim is 1 radian for every, if the distance here, 1 radian is the angle such that the distance around the rim is equal to the radius. So a little less than 60 degrees, 57.1 degrees or 0.3, I don't remember. Okay, there it is. So now that we know the angular velocity of the pulley, since the pulley is attached to the beam, I hope securely, let's just screw ahead of and tighten, make sure. We know the angular velocity of the beam. That means if we time the descending mass, we can figure out what the angular velocity of the beam ought to be if you use it to mass. It's right. Okay. So we ought to be able to do that pretty easily if we think through it. The other thing is, if we know the details of the motion of the descending mass, which we do, if we have good timing and good distance, what else can we determine about the motion of that descending mass? Now, if we count the number of rotations during the descent of the mass, what can we calculate? Well, we should know by now that you can really easily calculate how many rotations per second, right? How fast, what's the rate at which this thing's rotating, okay? If it rotates through, I just use the example, I think it's 8 rotations in 20 seconds. You divide 8 rotations by 20 seconds, you get 0.4 rotations per second. Okay? And that's a perfectly good angular velocity, although you really don't want to use it in most of your calculations. When you get into chapter 10, though, you have a lot of things. They're talking about revolutions per second. They're not talking about radians per second. Then later you get into things where you really need to do it with radians per second. Okay? But one is convertible to the other very easily. Or 2 pi radians of arc or of angle in a full rotation. Or if you want to do degrees per second, you can do that, but you really don't want to carry around the conversion factors. You just don't have a lot of conversion factors when you do radians. Okay, sometimes that doesn't matter. But if you want to figure out the kinetic energy of the magnets on the end of that thing, on the end of the beam, then you probably want to work in radians. Okay, you can work in revolutions. All you got to do is figure out the circumference of the circle, and you can multiply the circumference in meters by the number of revolutions, and you get the distance the magnet moves. Okay. And there's, well, I'll leave it at that. Okay, so now my question is, how nearly do you expect on this system that the number of radians per second you get at the end is equal to what's predicted by the radius of the pulley and the distance mass descends? It's because you know how fast the descending mass is going, you know the diameter of the pulley, So you should, what you get if you count the revolutions and figure out what the average angular velocity is, and then the final angular velocity, that should match what you get when you use the radius of the pulley and the speed of the descending mass. Is it going to match? Why might it not match? Okay, now we can also calculate the angular acceleration of the beam, assuming it's constant. Okay, then we get to the calculation of, or the question of, our results aren't totally consistent. They never are in an experiment. And then it comes to the question of why aren't they consistent? Okay, things get in the way here. The string is wrapped around the pulley. There's a fair amount of string wrapped around that pulley. So actually, the radius of the circle or near circle that's being followed by the point of the string that's unraveling from the pulley, the radius of that circle is not going to be constant. It's going to be actually a spiral. And that throws a monkey wrench into things. That's one reason our results might not be completely consistent. Now, what that does is causes the accelerations to not quite be uniform. To not have deviation from uniform acceleration, we've got to use calculus with that if we can figure out what the nature of the deviation is. We can approximate it. There's also things like friction, and we can measure the friction. We can measure the friction of the rotating beam by getting it in motion, counting the number of revolutions it takes to stop. Gives us a pretty good estimate of its angular acceleration under friction. Don't get it going too fast because their friction will start getting into it. But if you want to analyze what happens with the friction within the bearings, friction within the bearing axle system there, you deal with kind of slow rotations. Not too slow, because the system isn't perfectly balanced. Okay. And if it's not perfectly balanced, then it wants to go to the position where the potential energy of the system is lower. Meaning if one magnet has more mass than the other, but everything else is equal, that magnet's going to tend to pull the system down a little bit. It's going to tend to take it away from level. So as the thing rotates, that magnet is going to go up and down, and the potential energy there is going to vary with a revolution. That's something that's worth understanding and dealing with. Now, the main thing I want to focus on right now is just energy. So how do you account for the energy that's the potential energy that's lost by that mass? Again, gravity is doing positive work on it as it descends, so its potential energy is decreasing. Okay, energy is being conserved within that system. It's a pretty conservative system. Okay, where does that energy end up? Well, one place it ends up is on the magnets. Can we calculate the kinetic energy of the magnet at the end of the rotation, at the end of the descent? Well, yeah, if we get the angular velocity of the beam at that point, theoretically, or just by directly trying to measure it. Okay. Get the angular velocity of the beam, and we can figure out the speed of the magnet and its kinetic energy. That makes sense? Okay. Well, is that going to account for all the potential energy loss? Well, there are two magnets, so the potential energy, kinetic energy of one magnet isn't going to account for it, right? What about the potential energy of the two magnets? Well, that's going to come closer. According to my calculations, just that middle back of the middle envelope calculations, that's about half of it. Where's the other half? Well, some people say, that'll give you a chance to say, uh, where's the rest of the energy that's, okay, let's put it this way, how do we count for the rest of the potential energy? Magnets have a kinetic energy that's pretty close to equal to half of the potential energy loss. That is half of the work done by gravity as this thing descends. Right? Where's the other half? Well, I immediately got a good answer. The rest of the energy is in the beam. Well, not really the rest of it, because there is some loss of friction. So total kinetic energy of the whole system is going to be less than the loss of potential energy. The friction is very low here. Okay. So the two ought to be pretty close to each other. So just assume an ideal case, zero friction. Okay, we can test that by observing final velocities and all that stuff as we've talked about. About half of the potential energy loss is accounted for by the kinetic energy that's gained by the magnets. Where's the rest? Well, people say maybe it's in the beam. Okay, and then I said, well, that's kind of complicated. What is it that complicates the calculation of the kinetic energy in the beam if you know its angular velocity? And people gave me complicated answers to simple questions, but they weren't that complicated. They were right. So, and they're talking kind of low. There's background noise. I don't hear that well. I had to ask them to repeat a couple of times because there are a lot of words in there that I didn't quite understand until they were said slowly. So it comes down to, well, if it's rotating about this point, then the speed at a given angular velocity of a particle on the end of the beam is greater than the speed of a particle near the middle. So a given chunk of mass out here is going to have more kinetic energy than this chunk of mass in here. It is a continuous change in the kinetic energy per unit of mass as you move from the end toward the center. Does that make sense? But it just comes down to, yeah, particles near the center are moving slower, so they have less kinetic energy. Implicitly assuming particles of the same mass. And that leads us almost directly to the concept of moment of inertia, which would be a good thing to read a little bit about before Monday's class. Okay, because we're right at the point where we can start defining moment of inertia in terms of the system. And once you have the definition of moment of inertia and torque, those two definitions can both come out of energy considerations. Both reinforce the power of the energy model. And you get pretty simple explanation of torque and angular momentum, or moment of inertia. There's also angular momentum, which is a whole chapter in itself, which is kind of interesting. Okay, so let's talk just briefly about pendulum. And turn this off for the moment.